Okay, now that we have tried one problem out with angle-angle similarity, let's see if we can find any other uses. So, our following problem says the lengths in the diagram are as marked, and WX is parallel to YZ. Find PY and WX. So, parallel lines mean congruent angles. This has to be something that you have to understand. Parallel lines means congruent angles. And we can easily tell that this angle here, XWP, must be congruent with PZY. And if you are not sure why that is so, it is because they are both alternate interior angles. So I'm going to say XWP is congruent to the angle PZY. I'm just going to abbreviate alt interior. And again, the reason I'm finding these angles is because I can't really do much with this information until I know that I have two similar triangles. If I do not know that the triangles are similar, I can't make any ratios. So, are there any other ways that I can get congruent angles? Well, I think to get away from all the parallel line stuff, you could still use it, but I'm just going to note that this angle XPW and the angle here YPZ are the same because they're vertical angles. So again, we have XPW, which is congruent to the angle YPZ. And that's because they are vertical angles. Now, that has given us sufficient proof for angle-angle similarity. So now I know the triangle WXP is similar to the triangle, well, let's see, WXP goes from the marked angle once to the unmarked angle to the twice marked angle. So let's try to follow the same order. We're going to start at the marked angle, Z, then go to the unmarked angle, Y, and then the twice marked angle, P. And that will give us angle-angle similarity in our appropriate congruent statement in the proper order of letters. So now that that is true, we can come up with some proportions. So if we take a look, what seems to be the smallest side of WXP? Well, that seems to be XP itself. So, well, even better yet, let's start with what we're trying to find, PY. PY seems to be the smallest side of PYZ. So that would match with the smallest side of WXP, which is XP. And let's come up with some other ratios. So if we started with the larger triangle, let's use it again. So how about we use the largest number, YZ, for our next ratio. YZ, the 12. And a 12 would, of course, match with, if we look at our other triangle, well, we notice the 12 is the parallel line. And it seems to match with the other parallel line, WX. And finally, we have the side PZ. And PZ would, of course, then match with WP. Okay, so now let's fill out any values that we can. Well, we're trying to find PY. That's one of the things we're trying to find. So we can't really fill anything out there. But XP, we can. It's 3. Which is equal to YZ. Well, YZ is 12. And that is over WX, which is an unknown. One of the things we're trying to find. And that is equal to PZ, PZ being 10, and PZ matching with WP, which is 5. Now, you might notice this fairly quickly that 10 over 5 reduces down into just 2. So, let's take each of the ratios that have our variables in them. So the first one's PY over 3. And now we can just set that equal to 2, because that is what the scale factor is. That 10 over 5 just simplifies to 2. And by some simple multiplication, multiplying 3 on both sides, because we want to multiply by the denominator of our fraction, we receive that PY is equal to 6. So that's our first answer. Now we can take our second ratio, 12 over WX, and set that equal to 2. Well, we're going to do a similar thing like we just did. We're going to multiply by the denominator. The denominator being WX. So I'm multiplying both sides by WX, which means I'm going to get 12 equals, well, 2 times WX is just 2 WX. And to get WX by itself, we will divide by 2. And we actually end up getting that WX is the same as PY, which is 6. So this is just another example of how to use angle-angle similarity to solve for some missing sides of some triangles.